Good afternoon. My name is Daniel. I welcome you to our online training for students today. Today we have the third part of our RFEM series, RFEM for students. I am very glad to present you this training. As I said, my name is Daniel. I am responsible here at Dlubal Software for our German team. In addition, also for the marketing, and next to that, also a little bit for the customer support. Next to me is also my colleague Yannick. Yannick, if you can introduce yourself.
Yeah, also from me, welcome to our training session. My name is Yannick. I'm currently a working student at Dlubal, and I've been here for like 1.5 years almost. And today I will take care of your question and answer them as best as I can. So if you have any, feel free to ask them in the questions tab and go to webinar, and I will do my best to answer them.
Thank you, Yannick, very, very much. So for those who are using or attending this training for the first time, few words to our platform, go to webinar. So you have here your control panel. You can hide or show it here by clicking this arrow. When somebody can't hear us, then maybe it is because of your audio settings. So just go there, adjust it, change maybe the speaker, and then you should hear us. And if you have any question, don't hesitate to write us and Yannick will answer you these questions. So the content of today is we have 3 chapters. The first chapter we are going to begin with the modeling and design of a timber truss girder. Will be a flat 2D truss girder. Then we continue with the modeling and design of a steel hull with concrete columns, and finally we end this training with a design of the concrete building. You see it on the right side, and maybe some of one knows this concrete building. This was also part of the second training, the second part of this online training for students. So I think the modeling of this will be familiar. Okay, I think we can close our webcams and start the modeling in RFEM. So therefore, I open RFEM. This is also the concrete building where I will show you at the end of this training the design of the concrete slabs and the columns and slabs and also beams. And the first example will be this flat truss beam girder made of timber. Okay, so therefore I click here on new model in the symbol bar. I click here on new model and I click here model name, timber truss girder, and yeah, I will save it to my download folder. But you can also create a new project. I will use the 2D model XZ, so only vertical and horizontal deformation is possible. Note, no bending out of the plane or internal forces out of the plane. So we will have only 3 internal forces. I activate also the automatical combination of the load combinations, and I refer to the Eurocode, and the national annex will be the normal Eurocode. Okay, my positive orientation of the global z-axis is downwards, and let's press OK. I make here 2 because I have already done it. Okay, let's do 3 here. Now it works. Okay, Good. So again, to this training, as every training, this training will be recorded. You will get the certificate and also the materials to download, the models to download. And normally this training is also for doing it separately on a second screen when you are watching this, so you can do it together with me. I think it's on pace quite good for someone who is also doing this on a second monitor or screen. So you are welcome modeling with me together. Okay, so first of all, we create our truss girder made of timber. In RFEM, we have different possibilities to create this, but I would say the smoothest, the easiest, most comfortable is that we use here in the menu bar, the toolbar, and we let generate us a model which has a lot of members. So, and there we find also this 2D truss. I click on 2D truss and I will take here this type. So this saddle roof, and I choose here these diagonals, and the number of bays are 10. And you will also see how the image on in the left corner will change, and the total length will be a quite huge truss, will be 60 meters. The total height, let me take a look to my notepad. Yeah, 5.753 meter, side height 2.6 meters. Okay, so the next step will be also that we create also new cross section. Therefore, we click here on new cross section. So for the upper chord, and we create here this parametric timber cross section. It is a rectangle cross section. And there we insert the values of the width with, what do we have here, 220 millimeters, and the height is 520 millimeters, and the material is a timber material. In this case, glulam timber. Because we don't have it here, we have to create a new material. Therefore, I create a new material and I click here on the material library. And the material category group is of course timber, and then we filter it according to glulam. And there I choose the Eurocode definitions for the materials, and I take this homogeneous GL28 glulam timber. Yeah, 28 means that we have a banding, so a strength for banding of 28 Newton per square millimeter. So I will take it, double click, OK. Now when this warning appears, you can click here on OK. Doesn't affect your member structure. It's more when you are facilitating with, when you are dealing with some surfaces where the thickness plays a bigger role, has a bigger influence on the structure, but at members, this warning doesn't have a big impact. Okay, then click on OK. And we will copy here this cross-section description. Just mark it, right click, copy, and press on OK. And now we create 3 other cross sections. Now I will do it a little bit faster. So the lower chord, now we can copy it here. Sorry, not copy, we can paste it here. This will have a T-rectangle of 2020 and 560. And the material is again glulam timber. I click on OK. And the same we'll do also with the diagonals and verticals. Yeah, here for the diagonals, we have a rectangle of 200 and 200, so quadratic. And here for the verticals, we have a cross section of 200 and 180 in the height. Okay, then everything is done. Maybe important to know is that we have here 2 different member types. The one is the beam member type and the other one is truss. Beam means that all internal forces can be transferred to the other members and beams. And the truss member type means that it has the same behavior like a beam member type, but at the end of this beam you have hinges, moment hinges, so no moment bending moments in this case will be transported and transferred to the other beams. So these trusses are don't have any moments at the end. Okay, good. And now you'll see this nice truss girder, made of timber. And the first thing we want to do is that we want to delete these 2 members because we want to set up here our support. So I press the Control key on my keyboard and also press the left mouse and draw a selection window. And now I leave it and I do the same on the right side. Now both members, so in general 4 members are selected and I will delete them. So therefore I click delete on my keyboard or press also the right click and say delete. And after that it will look like that. Okay, so the next step is also that we make here these outer diagonals or struts to beam member type, because as you can see, when we have here vertical loads, this lower chord will transport these forces, and because we have here no beam type, that this will conclude that we can't import also no bending moments, and this is not good. So therefore we will change here these 2 outer struts and diagonals. So I will select them. Again, I press and hold the Control key in order to add something to my selection. Right click, and then I say, okay, edit member. And there I change the member type to beam. I click on OK. And now I want also that this lower chord have also this set of member. Again, what is a set of member? A set of member is where I can a summarization of all the members who are in one line drawn or created. For this, for instance, this upper chord here, when I take this as a reference, I see here these lines or these members, and they are one polygonal line, and therefore I can summarize it as one member, for example. And this is very good when I do maybe the load application, or when I want to see the results in a better way, or also for the whole design of material specific constructions. So I double click here on this set of member, and I will add the outer struts to my set of member. So therefore I select here the member, this one and this one. I click OK. Then again on OK, and now you see, okay, these two members were selected to my set of member. Okay, good. Yeah, the next thing is that we add also some nodal supports. So therefore I select here this node. I go here to new nodal support. I will leave it as a hinged support, so vertical and horizontal forces will be considered and also will be activated, because I activate the vertical and the horizontal deformation. This means they are closed, so they have to appear vertical and horizontal forces. I click on OK. And on the right side, I do the same, but in this case, and release in the X direction. So we have a sliding in X. So only vertical forces will be transported or will be activated here. Okay. So now you see also a little bit the grid and this. So the grid plane here, the grids, they aren't, they don't fit here with the size of my model. In order to adapt my grid to the size of my model, I can do one thing. Right click in the work plane and go to work plane grid snap. Click on OK. And this new window appears. And there I can say, okay, please adapt me my size of model or my number of grid points according to the size of my model. Should be dynamically. So I activate it, I click on OK, and now it looks like that. Okay, good. I will change the display option. So I will go here and say, okay, please do this solid transparent display model. I like this view more. Okay, yeah, this was the whole modeling, very easily done with the help of our tools generator, generate model members here, and so on. So the next step is the definition of our load cases and then also a load application. Therefore, I go here to new load case in the symbol bar. And here I activate the self-weight plus roof load. I want to consider the self-weight of the structure. The next load case is snow. So snow on the left side. I choose the right action category. In this case, it will be snow, considering the height under 1000 meters. And now I can also copy because I want to create a similar load case. containing also the snow as action category, but in this case, the snow will be on the right side. Okay, and last but not least, wind. It will be wind, but suction side. And now I will go the next steps a little bit through. So we have actions here. We have the permanent snow and wind actions. When you are when you design combination, load combination, action combination, and so on with a Eurocode, then you have this description of these different actions. So we have the permanent action, then also the variable actions, and the variable actions are snow and wind. Concerning snow, there we have to modify something, because now how they are defined, this will lead, because they have the acting alternatively, this will lead that they won't be combined together. So snow left only and snow right, but this is in reality wrong, because the snow can lay on both sides, on the left side and on the right side. So therefore I have to activate here the acting simultaneously. This will lead to that fact that both load cases, so load case 2 and load case 3, both snow actions will be combined in the load combinations together. Okay, let's take a look to the combination expressions. I don't want to consider the serviceability situations, because only the ultimate limit state. So I delete them. And now we can take a look to the design situation. Eurocode, maybe we have also some participants from other countries who don't have the Eurocode, but in Germany and in Europe, we use the Eurocode. We are very happy with that. And this is the design situation. So as I said, okay, we have this permanent action with this partial factor for permanent actions. In general, 1.35. Then pre-stress, but in this case, we don't have any pre-stress. And then the first leading variable action, and then all the other variable actions. Okay, so let's take a look here to the action combinations. Here we can see it also quite good. So here we have the permanent. So we have here this action combination description. So the permanent, the first variable action, and then the second one. And when I have all the other ones, the second variable actions, then I have also this combination factor here, this psi, of 0.60 and 1.50 times 0.60 equals 0.9. Okay, take a look to the load combinations. Again, what is a load combination? Load combination is combination of load cases to one bigger load case. So regarding the load combination 6, let's take here a closer look. So here we have 1.35 times the load case 1, because this is the permanent action. Then the other actions, in this case snow, and because we defined them as simultaneously, this resulted in that we have now both load cases of snow combined together, and then not the leading action, and here we have this combination factor with this partial factor. Okay, and result combination. What is a result combination? Result combination is summarization of all load combinations in this case, where I summarize all the results. So the calculation won't be run again. Only the results of the load cases will be summarized, and then I have the possibility to see the minimum and maximum values of my structure and of my results. Okay, I click on OK, and now we apply the loads on our structure. So I click here on self-weight, the roof load, and now I can also say you one advantage of this set of member when I do the load application. So I click here on new member load, and now I refer to my sets of members, and the load parameter is in this case 2.5 kilonewton per meter, and very important, I relate to my true member length. Yeah, because we have self-weight and it's always related to the true member length. This is important to know. Snow would be to the projected member length, and wind to the local axis of my member. But in this case, global related to true member length. I click on OK. And now, because I selected their set of member, I can only choose and select here this upper or this lower chord, because we want to do this for the upper chord. I click here my upper chord, and everything was done. Okay, let's jump to the next load case. Snow left. Easy doing. I select here on the left side all members of the roof. Then I go back here to new member load. And the load parameter in this case is 3.75. And now it's important to have here the projected member length. And as you can see here now, we have already selected the members, and the selected members appear here to at this box or field. I click OK. And where is my mistake? My mistake is that the load is wrong defined. So I choose here again the load. Doesn't matter if I have also some selected members here. Right click, and now I can see here this context menu, and everything which I have selected appear here now. And now I can decide which of the selected objects I want to edit. In this case, I want to edit the member load. So uniform, edit, and also, of course, global related to projected member length. So, okay, good. Let's do the same on the right side. Easy doing. Snow right, member load 3.75. Click OK. And now we're in section. There we do also new member load, and we select again here sets of members. Load parameter is 2.4, and now important, the local related to true member length is the local z-axis of my member. And because the local axis of my member shows downwards, I have to press here minus, because my suction goes to the opposite of my local axis of my member. Click OK. Press or choose the upper chord and close this dialog with right click or escape. Okay. Good. So the next step will be the calculation. So all load combinations were created. Now we can calculate it. Let's click here on calculate all. All load combinations and load cases will be calculated. And then we take a closer look to the results, to the deformation results, and then we will do the design. Okay, good. So I would say 3 major steps to evaluate and to validate also your structures. First of all, take a closer look to the modeling. Yeah, are all members connecting to each other? Is there something missing? Do the plausibility check. Yeah, do the plausibility check. You can do it here in RFEM. These classes, do the plausibility check. Which load cases? All load cases. And when the plausibility check said, okay, all data has been checked, no errors found, then the first check is done. Then the second check, take a closer look to the self-weight, to the load case, and take a closer look to the internal forces, to the results. So what do we have here? We have here this load, okay, then this deformation, okay. So deformation looks pretty okay. Maybe only the vertical deformation are the symmetric. Seems that they are symmetric. Maybe I change also the display of the deformation. So I go here to the display navigator, go to the chapter results, deformation, members, and cross-section colored. Okay, is the deformation symmetric because we have a symmetric structure? Yeah, in this case it's symmetric. 50, almost more than 50 millimeters seems okay. I think this is normal. So the deformation looks okay. So this will be the second check. Check the deformation. The third check, check the internal forces. Are the internal forces okay? So normal forces, first of all, normal forces, okay, in the upper chord we have compression forces. This is, I think, pretty clear for this truss. And in the lower chord we have high tension forces. I think this is also pretty clear because we transfer in the lower chord the tension and in the upper chord the compression, and both leads to the support. Okay, yep, looks pretty okay. Especially here in the middle we have the highest forces, and where it could be a little bit problematic, this will be here on the outer diagonals, because here we have a really small cross section. I did it on purpose because I wanted to optimize it afterwards in the design process. But here with more than 200 kilonewton just in the characteristic load case, this will be a little bit critical because I don't think that this cross section can carry so much loads. So I think we will increase this cross section. Okay, good. So the normal forces seems pretty okay. Next one, okay, well, shear forces pretty low because it's a truss. Yeah, it's a truss. So no high shear forces. And bending moments, also no high bending moments because, yeah, truss is mainly for the transport of normal forces, compression and tension. But we have also some bending moments, and in order to do also this check, if the bending moments are transferred, we can do the check. So I can see here, okay, the self-weight is carried. Also here, and the verticals, we don't have any moments. I think this is also clear because the moments of the diagonals results because of the self weight, and here because we have beam member type, there the bending moment is the same on the left and on the right side. Okay. Yeah, and then also check the support reactions. Last check, support reaction. Are they the same on the left and on the right side when I have a symmetric load and also a symmetric structure? Yeah, in this case we have the same vertical load. And also check here in the tables, check this one. Sum of loads and sum of support forces. Yeah. If there's any deviation, then check your model if you have done any mistakes. Yeah, in this case 0%, so seems okay. Yeah, good. So let's do the design. I think the most important checks were provided. When I do a material specific design of my structures, I always use here in RFEM 5 the add-on modules. So in the table, I will find the add-on modules. I go here to design timber and click here on RF Timber Pro. Alternatively, I find the add-on modules also in the in the data navigator. I close this maybe. I find here also in the data navigator on the left side all the add-on modules. In order to pin one add-on module as favorite, just click the wished add-on module with the right click and say favorite, and then this one is appearing there at favorites. Okay, double click on the add-on module RF Timber Pro. There we do our design of timber members and how I will do the design. First of all, I will do the design with the upper and the lower chord, then the verticals, and then the diagonals. Okay, so I choose here the sets of members. This should be here, this one and this one. Okay, the standard national annex should be here, only the Eurocode. Here, when I click here on this national annex settings, you can see here for the glued laminate timber that you have here different, this material safety factors, gamma M. You can also modify it, other settings, and so on. Yeah, this is also something what you can also. This is also something. This is also something that you can find in your standards. Yeah. Okay. Yeah, and then the selected, I will select all the load combination where I want to do the design. In this case, I decide for all load combinations. You can do this also for the result combination, but then I have a better overview of which load combination are the maximum minimum values. The materials, here in this case, the glue lamp timber appears. I have here an overview about my material properties. Go to the next chapter. Here, the cross section. I have 4 different cross section. Then the load duration. Here in this case, I want to change the snow to short term, as well the wind section, and for all members the service class is 2. Yeah, service class 2, what does it mean? Temperature of around about 20 degrees, and the mean moisture is under 20%. And very important, the relative humidity of the surrounding air only exceeding 85%. So it's the standard for normal roof structures. Okay, effective lengths. So when I'm talking about stability, I am also talking about compression. And now I do some assumptions. Yeah, it's also something you have to document when you do this. So I assume that on my upper chord, a lot of purlins are connected with the upper chord. So every meter, one purlin goes out of the plane and is fixed on the upper chord. And this will lead to that fact that we don't need to consider the buckling and the lateral torsional buckling. Okay, so I deactivate it. And as we already seen, my lower chord has only tension forces, and when I have tension, no compression analysis or no stability makes sense. Therefore, I deactivate it too. Okay. Alternatively, I could do the same here by clicking on details, go to the stability tab and uncheck the stability. Then this effective length will disappear. Okay, parameters at the moment not important, so let's calculate it. And now we have here the different results. So now I can filter the results by load case, cross section, set of members, and so on. I will choose here the cross section, and all cross sections are okay, except the T rectangle 200, 200. Do you see? And take a closer look. Okay, what is the problem? On axial bending about y-axis and tension. Yeah, I'm pretty sure that the tension forces is too high. So here we see more details. So first of all, the material detail, cross-section data, and design internal forces. So how much forces? So mainly the tension forces of 600 kilonewton is responsible for the design. So we do here this tension cross-section design mainly. And then we see, okay, our tensile strength is lower than our tensile stress when I also do it with a combination of the bending. So I have to do something. So what can I do? What can I do? So I can do the following. I go to the cross section and I say, okay, please optimize me this cross section. So I want to optimize it. The width should be the same like the lower chord. So 200, 200. Only optimize the height. Start with 200 because this was already the value which didn't work, and the maximum 440, and the increment could be 20. Okay, now the program will optimize it in the current row, and I want to have a design ratio of under 90%, because I don't trust the timber maybe so good as steel, so not more than 90%. So I click here on details, say go to the other. So when I do the cross-section optimization, max allowable design ratio of 90%, so 0.9, I click on OK. I click on calculation. And the proof is OK. This is nice. And now we can do the following thing. I know the T rectangle 2020, pretty good. I can say OK. Export cross section to RFEM. Yes. Because when I have in the design add-on module another cross section, then I should also export it to the main RFEM program again in order to calculate it. Again, because then I get also other internal forces and also other deformation. Okay, I click OK. And now I run the calculation again. And now I take a closer look again to the design add-on module. And now I see here the design ratio 0.9, pretty good. Okay. Everything under 1. And now we create new cases. First of all, I rename this case because this will good also for the documentation. So upper, lower chord. Now I create a new case because now I want to design the verticals. No, sorry. Okay, again here, I put all load cases on the right side. I choose the correct members. I select the members for design. Now I want to show you one interesting selection method. Click here in the symbol bar, select special. Go to members. And say, okay, parallel to member, choose the correct member, the vertical, click on OK, and all other vertical members are selected. I click on OK. Now I go the windows through, cross-section is clear, materials are clear, load duration is also clear here, just change it to short term. And the service clause is 2. And the effective length is in this case, the existing length of the members. So I will consider them as Euler beams, Euler case 2 in this case, because we have this, the buckling factor of 1. So this will be the buckling length also. And now I can calculate it and take a look to the results. Seems pretty okay. Perfect. And now I do the same for the diagonals. Put all my low cases there, and there I have to select the correct members. This time I show you another selection possibility. I go here to the View navigator, click here on View, And then I go here to members by cross-section, and then I choose this one. I click OK. Again, here I will consider the short term. And the effective lengths, the same like at the verticals. We have the member length as buckling length. I calculate it. And everything seems okay. Very good. I can also filter the design ratios. Say max, put me the max maybe here, cross section. I see this one. Or I can define it also. So sorry. Then all design ratios will appear who are bigger than 0.5. Okay, good. Yeah, I think this was the design of a timber truss girder. I think you get a good overview of how create, first of all, this structure very easily and very fast, how to do the load application, how to deal with the load cases, load combinations, and also the actions. And then you will also get an insight of how to evaluate the results, deformation, internal forces, and finally also the design. Okay, Yannick, are there any questions, or should I show something?
As far as I can tell, there are no questions, so we are fine.
Okay, yeah, to the people who are attending this training, don't hesitate to ask us. You feel free to ask, don't be shy. We are glad to help, okay? So I would say let's do a break. We will do a break of 8 minutes. We will see us at 50 or 3 p.m. Okay? See you later. Okay, Yannick, are you here? Can we continue?
Yes, I'm ready, man.
Okay, very good. So let's continue. The second chapter is the modeling and design of a steel hull. So therefore I go here again to new model. And I insert here steel hull students, save it under my download folder. And now important thing, type of model is 3D, okay? And yeah, the rest pretty clear. Eurocode, national annex, the real code one, global z-axis is downwards, and also I create the combinations automatically. Okay, I click on OK. And the first thing I do is also using the generate modeler or the modeling, the generator of my modelings. Yeah, again, go here to tools and generate it. So because we do now, first of all, the flat frame, I will go here to the work plane XZ and want also to have the view against my global Y axis. So view in reverse Y direction. Okay, and now I go again here to tools, generate model members, to D-truss. Here I have this saddle beam again, this diagonals, and the number of bays are 6. Total length 80.75 meters. Total height 3.25 meters, and the side height is 2.75 meters. Okay, so now I will create again 4 different cross sections. The upcourt gets an HEA 300 profile. I click here on HEA 300. Material is steel S235. Click OK. And now I will copy here this one. Control and C. OK. And I will do the next cross section for the lower court. HEA 280, material steel. Okay. The diagonals get another profile, in this case an IPE profile, IPE 160. Here we can see also the cross-section properties. You can set up the color. I can show it to you afterwards. And the last cross-section, the verticals, get a cross-section of HEA 160. Okay, also here material is steel. I click on OK, then again on OK. And now I have here this truss. Okay, so what's next? The outer struts, I want to, now I'm looking for the English word. honestly. What is the English word for that? Yeah, I want to replace it. Sorry. The outer strut diagonal here, in this case, I want to replace it by another cross section. So I will select them both, right click, member, edit, and I create here a bigger cross section. In this case, what I have here, HEA 140, no IPA, because there will be higher forces. So therefore we increase the bending capacity of this cross section. Okay, so now we have this truss here, and now I want to display it according to different colors. Therefore I can use the display navigator here on the left side, go to colors and graphics according to, this is almost at the bottom of this display navigator, and now you can say, okay, show me please the colors according to my cross sections, and here I can see the cross sections. If you are not a big fan of the color purple, for example, no problem. Go here on the right side, double click on the color and change it to your favorite color. Yeah, I say, okay, yeah, dark green is pretty okay. Then it looks like that. Or alternatively, you can do this also in the member function here. Go to the cross section here, go to edit cross section and change here the color to, I don't know. Yeah, let's do orange. Okay, good. Then we have here, this one. Yeah, and this was only for this one member. Now we do it also for the other ones. This. And now. Okay, good. Yeah, we have also the possibility to show us the colors in other graphics like member type, member hinge, and so on. But this is something we don't have until now. Maybe later we will do the same with the member hinges. Okay, so how we move it 8 meters high. So we select everything, right click on the whole structure, we say move and copy. And we only want to move it, so we don't need to insert here any number. Just say here -8 because reverse the Z direction. Now we delete the outer and verticals because we want to replace them by a vertical concrete column. For the vertical concrete column, I will add here a new member. So I click here in the symbol bar, new single member. I create a new cross section, and in this case it will be a quadratic massive cross section, 650 millimeters by 650 millimeters. I activate here in the status bar the snap function. Sometimes I deactivate it, then I forget it to activate it again. Now I activate it and I draw my column from the bottom to my left corner, upper corner. Okay, good. The next thing is creating this concrete column on the right side. And now you see we don't have any grid points here at the X coordinate 1875. Now there are different possibilities how to solve that. In my opinion, the easiest way is just copy it via drag and drop. So doing this, select the concrete column, also the upper part, then press the Control key on your keyboard, press the left mouse click, and via drag and drop you can easily copy it. Remember one thing, use this function. This is so easy. This will help you in modeling things in RFEM and so on. Honestly, my favorite function in RFEM. Okay. Yeah, so the next thing is the definition of hinges. So we want to have here hinged connections. First of all, we want here the hinge connection in the left upper corner and also here in the left lower corner. In the left and the right lower corner, we want to have such hinge definition that we don't want to transfer any loads to the concrete column. All the loads should be transferred via the diagonal, the outer diagonals. Okay, so how to do that? In general, we have two ways to insert hinges in RFEM. The first one is create the hinge in the data navigator or also in the menu bar models. Yeah, so I go here to member hinges, right click, new member hinge. Then the first one will be a normal moment hinge. In order to create a moment hinge, I have to activate the rotations. Alternatively, I can do this also with these icons. So when I want to have a normal release or a normal hinge, and I click here on the set XL release N or moment hinges, these icons. Okay. Normally the hinges are referring to the local member access, except the scissor hinges, but to the scissor hinges I come later. So I click OK. Now the member hinge was defined, but isn't assigned to any member. So this is also the reason why this member hinge appears with a blue color. In order to assign it, just right click and now say assign graphically to members. So now you see here different blue nodes, points, and when I drive through one of these members and I am in the middle of one member, then the hinge will be created on both ends. When I'm only on one end, at the one end, then only on the left side in this case, and here on the right side. So in this case, I need it here on the left side and then here on the right side. Okay, moment hinges. So the next way of inserting hinges is double click one of the member and define the hinges here in the member addition, or definition. So create here also a new member hinge. And then say, okay, you want to have moments. And I also don't want to transfer any shear forces, so UZ, and no normal forces, UX. Okay, click OK. And the same thing on the right side. Okay, so now we add here some support, nodal support, new nodal support. In this case, we want to have a rigid, so all moments and all normal shear forces will be activated by this support. Okay, so the first frame is ready. Let's do a basic calculation and take a closer look at the results here if we have modeled it correctly. So I create a new load case. Self-weight plus that load. Self-weight is activated. Click on OK. And then we show the results. And we see here a calculation error. Okay, so this is maybe because of the definition of the wrong hinge. This is no problem. So when you have something like that, then the first step is to put the hinges away. And then calculate it again and then see, okay, has it something to do with the hinges? Okay, now we have another problem. Here again, a problem. So also here we put the hinges away. And now I can say you also the problem. The problem is that we defined here, let's calculate it again. And I think we have still the same problem. Okay, this can't be possible because now everything is almost has a rigid connection. And I can say you now the problem. The problem is that we defined here this member as member type truss. And this is a problem because this should be a beam. So how to fix that? I select every beam here, click on edit member and change it here to beam member type. Okay, now I assign again the hinges. So I click here, this one. Oh no, easier. I right click here, this one. This was with the different hinges. Now you see this is by far faster than assigning it by the member. Now let's do this again. And now we have finally the results. Yeah, so mistakes, errors happens every day. No problem. The most important thing to do is to find them and to solve them. And how did I do that? So first of all, okay, I thought these are the hinges. I defined them wrong, but this was not a problem. Then I checked the member type of this column or of this beam, and I detected that it's a member type truss. Yeah, and as you know, member type truss has on both ends hinges. And when I have here a hinge, and then again here a hinge, then I have problems and troubles to transfer my loads up to my button. Yeah. And this was also the reason why I found it. Okay, so next thing, check, plausibility check. Okay, vertical deformations seems okay. Member, are my connections okay? Okay, 0 moments, here again 0 moments. So the member end hinges are okay. Take a closer look to the shear forces. Also here the shear forces are transferred to this column. And now, most interesting thing, the tension forces of this lower chord are transferred to this outer diagonal into that column, that we get here compression forces into that column, and no other forces are transferred to that connection. So this is good. Okay, yeah, short check. So the next thing is, what else? What do I have here? Yeah, of course, again, then I can adapt my work plan to the size of my model. This is something I will do now. And then I will copy it out of the plane 2 times. I select everything, right click, click move and copy. Number of copies are 2, and the displacement vector is in the global y direction, 9.5 meters. Okay, I draw my view a little bit. I change it to the web plan XY. And now I put some purlins, and they will connect my frames together. Okay, so therefore I create a new single member. This purlin will have a cross section of an HEA 240 and will have on both ends hinges. So first of all, I create a new cross section, HEA 240. Steel, of course. And member hinge, both member moment hinges on both ends. So I will create them once here, then at the first, I hope first is the correct word for first in German. I'm not sure, but I hope so. But yeah, and you know what I mean with here in the middle of my roof. And also on the other side, Okay, yeah, the next step is creating the purlins, the other purlins here at the other nodes. And therefore, I do only a member start hinge. Because we want to do for the now created beams another hinge, scissor hinge. So I select all of these purlins, put them to the other side by drag and drop. Now I had to define them again. And now, very important thing is that we do the scissor hinges. How to do a scissor hinge? Again, I define a new hinge, new member hinge. And there I will activate some hinge conditions. So, first of all, the scissor hinge is only possible when I refer to my global coordinate system. And I have to activate here the special type of hinge. So I don't want to transfer any normal forces into my upper chord. Therefore, I activate here the hinge condition UY, YUY, because I refer to my global system, and normally the local member axis, the x-axis, is the same like the global UY condition. So I activate here UY. And the hinges, I activate all moment hinges, so I also don't want to transfer any torsion. And important, when I want to activate here, I have to set them as special. Okay, I click on OK, and then I will assign them. So assign graphically, I will have them here and here. And here, I click OK. Now I have here the scissor hinges, and now at the end of this 4 beams, I want to create another member, and in this case it should be this hinge definition. I activate all moments because I don't want to have also no torsion, and also UX because I assume, okay, this hole can be enlarged, so therefore I will give them this release. Okay, so now I will say you also can give you also what it is about this this scissor hinge. I will calculate it, only the self weight, and now I can briefly explain what I'm talking about when I talk about the scissor hinges. Okay, again on problem. I will do the check, the different member types. Okay, seems pretty okay. Then I will do the check of the hinges. Let's do the member hinge check if there are any mistakes. And this seems also okay. Yeah, of course, what I forgot is bracing. Bracing also is also an important topic. Therefore, I create a new member. Member type is in this case tension. So we get a non-linearity in our system by adding this bracing, because the bracing is only activated when it gets tension forces. The cross-section of this bracing is a rolled cross-section with a diameter of 20 millimeters. I click on OK. Again here, OK. I deactivate here the snap on the grid points. Okay. Take a closer look. And now who can see the mistake maybe? I have forgotten here to add one scissor hinge. No problem. So now this was fixed. And the next thing is the calculation. Before we calculate, remember these tension members, so this bracing, they are responsible for the stiffening of your roof structure. Yeah, and sometimes it can happen, like in my case, that it don't calculate, although you have the feeling that you have the stiffening there. Therefore, you have to go to the calculation parameters and activate here the exceptional handling. So when we are talking about the reactivation of failing members, in this case about this bracing. So, and I would recommend you put it here, failing members to be removed individually during successive iterations. Okay, now it should be calculated. I hope so. Yeah, okay. It's a good sign. Yeah, perfect. Yeah. So now we take a closer look to the scissor hinge. And take a closer look to the bending moment. Maybe you see here this distribution of the bending moment, and here you see at the short members kind of linear distribution. Yeah, in this case, it is not wrong, but the view or the visibility is a little bit strange. And this is because normally at the result distributions, the longest member will be divided into internal 10 into 10 units, and then at every one there will be one result. And if you take the longest and compare it to the shortest member, then it will be a little bit confusing. No problem. You can go here to the calculate function, to calculation parameters again, and click here on the number of divisions of members for result diagrams and put it here to 30. Then the whole system need to be calculated again. No problem. We calculate it again. This will take some time. And now you can see here a really nice distribution of these scissor hinges. So when I'm talking about scissor hinges, what I have done here, I defined this longer two-field beam so that no bending moments are transferred to the other or to the upper chord. Yeah, this is very useful because normally when I connect four members in this case with each other, they would be combined together and all internal forces would appear to the other one. And in order to consider the whole, also the clear structural behavior of a two-field beam, yeah, then I have activated here this scissor hinges. Okay. So you can see it here now a little bit better. I have here this support moment at the upper chord, and you can do things like that. Yeah. So in general, with scissor hinges, you can model the crossing of beams. Yeah. So for example, we have here this four members connected in one node, and each of the two member pairs transfers moment in its continuous direction. Yeah, and the continuous direction is in this case this direction of this longer beam. So the scissor hinges don't transfer any moments to the other pair, and this is something what I wanted to do and realize with the scissor hinges. Okay, good. Yeah, the next step is the load application. Load application, I close the visibility mode, load application. Okay, so I have here one load case. I will add 3 more. Therefore, I go here again, click on new load case. And the next load case will be the imposed load. We have the action category A. I create a new load case, in this case, snow. And the other one is wind in plus X. Oops. Wind in plus X. Of course, the action category is wind. Okay. So for the first load case, we apply following loads. First of all, the surface load of the roof. Therefore, we have also a very nice feature or function you find here in the tools. We can, next to the generation of model, kind of regarding members, surfaces, and so on, we can also generate loads. And therefore, I want to take this one from area loads on members via plane. So we will define now the plane should be flat, and there I decide to have the global related to area because we have the self-weight. The magnitude is 0.5. And now I choose here the correct coordinates. This one, this one, this one. I click on OK. And I deactivate the members, in this case the upper chord, because I want that the whole roof is carried by the purlins. I click on OK. And the same thing we will do for the right side. So again, tools, or another tip, when doing the same commands and so on, just click Enter or the return key on your keyboard, and it will do the same command or function you have done before. That is very practical. It's very helpful. So I choose here again these nodes. I click on OK. Deactivate or remove the influence of the upper chords and press OK. So pretty nice. Right click on one of the surface loads. You can display the member loads separately, and you see it here. Okay, good. Then we have here also an additional surface load on the lower chords. Therefore, I use the same function, generate loads from area loads of members via plane. And now I choose here this one, also this one, and this one. I click on OK. And the magnitude is here again, 0.5. And now I jump to the next load case, import load, and now I have a big advantage of this one because the program remembers the last input of this boundary lines or corner nodes, and the only thing I have to do is just click on OK, and I have created the load for the load case too. Okay, the third load case is snow. I want to show you on our website an interesting thing. Just give me a second. I have prepared here our GeoZone tool, load zone tool, where you can read all characteristic snow loads, wind loads, and also earthquake loads for your region. So when I click here on solutions, I click here on snow load, wind speed, and so on our website. And yeah, let's take, for example, not the United Kingdom, but yeah, my university, for example, in Germany. And I enter here the location of the Technical University of Munich. It will appear here. I can also zoom in. I have here this snow loads. I have here this characteristic value of snow load, the 1.15, and also here the different snow load zones. So what you do after this training is take a look to our website and search for your characteristic snow load in your region. And if you don't have any snow, doesn't matter, use the wind. Yeah. So I think we have someone of, when I take a closer look to our attendees, maybe someone of Italy, So go here to the standard, put here standard, Eurocode, and now Italy, and look for the seismic. Yeah, because especially in Italy, there are a lot of earthquakes, and also the ground acceleration is much higher than in Germany. So maybe someone is of, I don't know, Bologna. or Florence, let's say Pisa. Yeah. Then I click here the region and I get here this ground acceleration. Yeah, nice tool. So your homework will be after this training, check your snow load, wind speed, and seismic load for your home region. Okay, good. Yeah, back to RFEM. We apply now the snow loads. Therefore, I will also use this tool, generate loads from snow loads, do a pitch roof. In this case, I take this zone number from Munich. Altitude is 540. Ground snow load is 115, and this is the same like we had in our zone tool, load zone tool. Yeah, and now I have to define the roof geometry. So I take here this corner, this one, this. Yes. Constant, please, and also only the purlins. I click on OK, and then I press the OK button again, and I will see my snow loads. Okay, yeah. Next step, the creation of the wind load cases. Therefore, I use again generate loads from wind loads, vertical walls with roof. This is also something which is in the Eurocode standard implemented. So therefore, we have also this function. I go here to inland lands, info about wind zones. I choose here again Munich, double click, and now I have to define the base geometry, and then after that, the roof type. Yeah, and here an interesting note, please start with the right order. So when I start here with y, e, then you have to start it here, yeah. So I start here, and when you define then your roof geometry, you have to begin also at the same corner, so in the height at least. Okay. Then we will remove the influence from the whole truss, and also again from the upper chord. Okay, good. Click on OK, and the wind load is generated. So now take a closer look to the correct direction. The direction must be, because we say, okay, our load case is wind in plus X. Therefore, our load case definition, so the wind should be also on the side from AB, like that. Okay, click on OK. And now we will do the same wind load cases, but from other sides. And therefore we can copy load cases very easily. So what we are going to do is go here to load cases, open the load cases, and say copy load case. Click on the load case 4, copy load case, make this one as -X, do this now as plus y. And this one as minus y. Okay, now let's go through the load cases. And now we have here this load case minus x. Double click on this load and set it to the opposite side. And this is this one, DE. Okay. Now the other one. So wind in plus y. So should be this side, DCB or BCD. And the last one is this one, EFA. Okay, now the whole load application is done. Good. Yeah, let's calculate it. Calculate all. Load case 7 is not assigned to any action. Do you want to generate the combinations anyway? No, there's one mistake. I will cancel the calculation. And I go here back to the load cases and combinations. And here at wind in minus y, this load case isn't assigned. It's not assigned to any action. So I have to put it on the right side. Now it's done. And now we can calculate everything. Okay, this will take some time. No problem. I will drink some water. Okay, I'm back. The reason why the calculation took a little bit longer is because we had here the combination expressions also of the serviceability states, and they will result in more load combinations. And this was also the reason why it took a little bit longer, as you can see here. But doesn't matter. Now we take a closer look to one of the to the snow load maybe. We take a look to the internal forces. That looks pretty good. Yeah, also maybe the normal forces. Okay, how the snow forces are transferred. So we have here compression forces in the upper core, tension forces in the lower core, pretty high, and they are transferred to the columns. Mainly the columns will carry the whole normal forces. Okay, good. Yeah, next step, design of members. When doing design, you have the possibility here on the left side to use our add-on modules, and for especially in steel, for every standard we offer new add-on module. So we have this RF steel EC3. This means design of steel members according to Eurocode, but when we taking closer look to America, USA, we have also the design of steel members to the AISC, also British standard, Canadian, and so on. Swiss, but in this case we do it according to the Eurocode. So double click on RF Steel EC3. I separate it in two cases. The first one will be the whole cross-section design, so only stresses, no stability, only stresses. And the other one will consider the stability of one upper chord. Okay. So I will design here the members. So I have to choose the correct members. Therefore, I select the members to design. And I choose here all steel members. Therefore, I have to filter them. I can do this very easily by clicking here this view navigator and activating here this correct filter. In this case, members by material, steel S235. I choose everyone and I click OK. The national annex is the Eurocode. Take a closer look to this one. I have here this different partial factors. In Germany, we have, for instance, this for member resistance to stability failure 1.1. In the normal Eurocode, we have here this 1. Okay. So the next thing is what we do is take this result combination, because this serves as a summary of all load combinations, and do the cross-section design. So only stresses, only stress design. So go through the chapters. Material, I think it's clear. Cross-section, also clear. Intermediate lateral restraints, we don't need. And here, effective lengths, we don't need to, because we don't do any on any stability design. Therefore, I click here on stability, or sorry, details, and I deactivate the stability analysis. I click OK, and I run the calculation. Yeah, and the checks look pretty good. So I take a close look to the cross sections, and I see these things here. Maybe when I do the normal, banding. Let's take a look to that one who has the most. This one, cross section check. HEA 140. Which one is it? This one. So there you can see, okay, which design was done. In this case, the cross-section check, bending, shear, and axial force, according to this chapter. This is also this one you will find in the standard. So here you have the material properties, cross-section properties, also in which cross-section class they will be defined. Here the cross-section classification. In this case, we have no compression. So they will do the design and so on, and do the proof, and this will be the design formula. Okay. This is also something you can prove with your hand calculation when you take this beam with that internal forces and do the design. Okay, but this was very easy, just a cross-section design according to standard, no higher sign, no higher signs. So this was the case cross-section. Now we do the stability design. So therefore I create a new case. And now we say stability design. And for instance, we only take a look to the middle upper chord. Therefore, I design it according to a set of member. I would also recommend you doing this because it's easier to set up also the boundary conditions of this set of member. Material is clear, cross sections clear, intermediate. We don't need this. So now nodal supports. We see here this upper chord, and when we take a closer look to the local coordinate system, we see this one. And there we see here this different supports. Yeah. Currently, it has two supports on both ends. They have these conditions. We have a lateral support, uy, so in this direction. You see also here this direction, this according to this coordinate system, and also the rotational restraint bx around this x-axis. Okay, so we'll leave it like that and run the calculation and see what happens. It is not designable because the minimum amplifier of design loads, this alpha crop, is below 1, and this is not possible. It's because the length is pretty too long. So we have to add here an additional lateral support. So I click here on support number. I choose here the number at the first of the upper chord and only activate here the lateral support. I run the calculation again. Now you see it here also a little bit in the window, and the proof is okay. We can take a closer look to the mode shapes, and this is very interesting how it looks like. Here we see the restraints of the lateral support and also the support around the x-axis. There we see here a kind of warping, and here only the lateral support, no warping here again. Okay, so please consider these things, and then everything is fine with your design of steel structures. Okay, so this was the second chapter. Yannick, are there any questions?
Yes, actually there are. So not really directly to the task you just modeled, but there were some questions in correlation with timber structures, and especially with joints, timber joints, because we have one student here who keeps getting error messages and asks if we have time for a short timber joint example. Is this possible?
Yeah, but very short. So when you want to do or when you want to perform timber joints, you have to use our joints add-on module, and I will do this for this node here, for example, okay? So therefore, I go to the add-on module. The add-on module's name is joints, RF joints, design of joints. double click, and there I can decide if I want to perform or do steel or timber designs. So in this case, I want to do timber. And of course, here are only steel to timber connections possible. So this normal timber to timber is for very light structures. I put one purlin on the other, or I want to connect them, but with that high loads, only steel to timber connections are possible. And then you can design which joint category you want to use. Bolts, nails, screws, in this case, dowels, I hope I spell it correct, are possible. And then you see here this cutting situation. And we have also here only with continuous member. So we have this situation. Then you can also do here some other additional settings. And then you choose the correct node. You choose this one. I click OK. Yes. And now I have to define here some things. So I see here the different member numberization. So member 15 is the main member. Member 16 is the continuous member. And the other one are the connected members. And okay, this looks pretty okay. So let's do the loads. I will take just this one, doesn't matter. Oh, this one is better. Load duration, yeah, it doesn't matter. And now let's come to the geometry. And this is something where you can design and define the whole geometry. Now you can add here some diameters of the dowels, 18, 16, 12, and so on. You'll see here the number of rows, the number of columns, put here plug lengths, and so on. This is everything possible. Also the number of steel plates, I would recommend using just one, because then you don't have enough timber. Yeah, and then run the calculation, and then probably you will have to do some other optimization because of this. Yeah, timber cross-section, tension, bending in net cross-section. Yeah, then you have to some optimization and optimize your connection and so on. Yeah, but this is possible, of course.
Okay. And then I have one more, because you know more about this than I do. It's about the laminars that were before this, so part 1 and 2, because we have someone in here who missed those. Where can they find the recordings of the previous seminars?
Yeah, of course. You can find all recordings here. Go to education. I will post the link then to the chat. Here on the online training recordings. And here you find the last online trainings for students. Here, this one, RFEM for Students Part 2. And here, RFEM for Students Part 1 from April, and this from May. And today we will do this for June. Okay, I will share the link.
Perfect.
Another question, Yannick?
It seems like we have done it all. So no more.
Yeah.
Nice. and your opinions on the football match this evening.
My opinion, how the Germans will play against the French team. Of course, Germany will win. What do you think, Yannick?
A tough match, but I think we will win this closely.
Yeah, I think so too. Yeah. Okay. If there are no questions, then I would suggest that we make a short break of 5 minutes. So at 4:15 we will continue with the last example. Okay. So Bis später. See you. Okay, Yannick, are you here?
Yes, I'm back.
Okay, guys, I have something for you. I have prepared one survey for you. Please answer it to us.
So we can finally solve this.
Okay. I show you the results. So I think this is pretty clear. So we will win today. Yeah, good. It's a good sign for us as German football team. And yeah, I think we will win too. Okay, yeah, good. So last example, last 30 minutes, I will do the concrete design. So this is the model of the first, of the second training. I have already, yeah, this is something we have modeled together, and now we will do the design of the surfaces. So it will be a very easy design, yeah, and also take a closer look to the columns and to the beams. Okay, first of all, I want to have these two members as a set of member. Therefore, I select them both, right click and say, okay, create set of member. In this case, downstand beam. I click on OK. And the next thing is that we, okay. The next thing is that we do the design of the surfaces. Therefore, the whole surface things or the whole concrete things are done with the add-on modules concrete surfaces and concrete members. If we want to perform a punch analysis, so punching shear design, or also do the Foundation Pro, you can also design point or single foundations. So I click here on concrete surfaces. And other than in the other add-on modules, we don't define here the wished members or something like that. We define first of all the reinforcement templates. So in this simple task, we say, okay, please do the result combination as the ultimate limit state. The serviceability we don't need at the moment. You can do it, but as you know, this takes more time, this method of check, because you can decide if you want to have the analytical solution or a nonlinear solution. And when you want also to consider creep and shrinkage, then the whole calculation process takes longer. But in this case, only the ultimate limit state is important for us. I have here an overview about my materials, normally concrete C3037. This is also part of the modeling where you have to define the material, and the normal reinforcing steel is automatically added here in this add-on module. Okay, yeah, good. Of course, here an overview of the different material properties, I think pretty clear, yeah. Surfaces, here an overview of all surfaces with the thickness, and now we can do the reinforcement templates. So the first reinforcement template will be the slabs. Therefore, I put here slabs, and I apply them also only to the bottom and to the bottom surface. Oops. And to the normal slab in the first floor. Okay, only these three surfaces. then I have the possibility to set up here some reinforcement ratios, but in this case I don't need them. I can set up the reinforcement layout. In this case, the number of reinforcement directions are normally set to 2. Refer to concrete cover, some settings like that. I can also set up the concrete cover for reinforcement when I take a closer look to the exposition classes. Sorry, not exposition classes, exposure class. So I can find here these different situations. So when I take here XC3, then the whole minimum cover of reinforcement will increase. Also here, aberration class, and so find also better explanation of these things, and this for the bottom side and also for the top side. Okay, good, but in this case we'll leave it here with 30 and 40. Here the same. And of course also the reinforcement directions related to the local x-axis of image F element for results, perpendicular. I think it's okay. Good. Next one, the long, this is a difficult word for me, longitudinal reinforcement. I can't spell it. I hope it's okay. Here I want to have meshes. No, sorry, I don't want to have here meshes. I want to have here, the reinforcement area due to rebars. I can define it. So I say, okay, the spacing should be please 200 millimeters, and then you see automatically how the reinforcement area will be calculated depending on the rebar diameter and the rebar spacing. The rebar diameter is in this case 10 millimeters, rebar spacing 200, and please on both sides, so the top and the bottom, and also in both directions. Okay, click on OK. Then we will leave it, and then we make a copy of that and make the walls. And now you see also here the other walls, they were selected, and there we do a mesh. So we have also here this library, reinforcement library, and I take the Q mesh. So in both directions we have the same the entire cross section per meter. So Q 257, both sides. I click on OK, and now we see it here. Of course, we can also set up the additional reinforcement, but I don't think that we need so much additional reinforcement. And now jump to the next to the next tab. There you can adjust some things, but it's up to you what you want to define here. Minimum reinforcement belongs more to the general Eurocode 2, and the only thing I will do here is the design method, and I will do here no optimization of the design internal forces. And now we can take also a closer look to the details. Options, mixed method, reinforcement. But the concrete design is very, I would describe it as very not complicated, but not so easy to understand, because it's very tough in comparison to other design materials like steel, timber, and so on. So there are so many information in the online manual which you can read, and I would also recommend you, if you are interested in more the deeper theoretical knowledge, then take a closer look to the online manual or also to our website where our support engineers and other engineers write a lot of technical articles. You will find this help here with the button F1 or here on the left corner side. Now let's calculate it. So this will take a little time, sorry for that. The concrete design take a little bit time, especially actually my tablet is not the best one for running calculation. So I'm sorry for that, but yeah, 1 minute, then we have this. Yeah, it will take some time. I'm really sorry. I don't know why. Yesterday it took also a lot of time, but then we have it. Yeah, because it's always depending on the FE meshes, how fine the mesh is, and how many points it will conclude. Because on every grid point or every FE mesh node, there are results and they have to be calculated. Okay, now we have the results finally. Yeah. And first of all, general overview about the required reinforcement. So we see here the required enforcement at some places, some points, basic reinforcement by surface and by point. Yeah, this is a general overview in the tables, but yeah, I'm a big fan of graphics. So I click here on graphics. And in order to see or to divide the overviews a little bit better, I click only the upper, the slab on the top. I activate here in visibility. And take a view in the Z direction. Normally you will see it like with the ISO bands. So like that. Now let's go it through. So here I can see the required reinforcement. So wherever I see the blue things, I don't have to add some additional reinforcement. And when I put here this one, then I see here, okay, here I have to put required additional reinforcement. So actually you can see here, especially in the columns, at the columns, I have to put here some additional rebars when I only take provide. Yeah, here I can see the provided basic reinforcement in this direction. Also here for each FE element. And now show the reinforcement direction in both directions. So again, here the required reinforcement in this direction. So this is the top. The direction goes along the x-axis, then along the y-axis, and then in the bottom. In the bottom, we will see the field moments. Yeah, here. So I have to put here my reinforcements along the x-axis and here along the y-axis. Okay. Also the shear reinforcements. So especially at the columns, you should consider it a little bit with. So I would recommend you doing there also punching shear design, because it can maybe possible that this will be a problem. But yeah, the slab is 30 centimeters thick, so maybe it's also no problem. Yeah, but this is something you have to decide. Yeah, and this is basically the most important things. The required reinforcements you can check. Also other things here, design internal forces, normal forces, values on surfaces, and so on. Yeah, there are so many things to discover, but this is the most important thing. Also, maybe one interesting note is this thing is, let's take here a closer look to the required reinforcement. And I say, okay, show me please only the really required reinforcement. Then I see it here. So these are the places where I have to add something. Okay, good. Slab design. Next thing. Next thing is the beam. Downstand beam. So I cancel my visibility mode, go to the isometric view and activate here the RF concrete members. So again, we choose here the result combination. And we don't run any nonlinear calculation because this would lead to too much calculation time. We will leave it like here. Materials, I think this is clear. Cross section, also clear. Ribs. Now, because we have this member type is a rib. What is a rib? Rib is a member with an eccentricity and also the integrated widths. So normally we have only here this small member, but because we have here this downstand beam and also with this effective widths, also like a T-beam, yeah, like a T-beam, the internal forces in the surfaces are also considered in this beam. Okay, there we enter the same effective widths. And now we define the supports. The support is once here at the wall, here at the wall, and then here at the column. I click on OK. And of course, they should have a monolithic connection, and the end supports are on both ends. Okay. Yeah, of course, you can set up some additional things here at the supports. You can consider the limited moment redistribution of the supporting moments. You can reduce the moments of a monolithic support according to the standard and so much other things. But for this easy example, we leave it like that. Now, let's come to the reinforcement. Therefore, I do here this one. First of all, the reinforcement group. This will be the downstand beam. Members is no members, only the sets of members, and which diameters should be possible. In this case, the diameter of 20 millimeters and 25. And all the other things we don't need, so we can leave it like that. Number of layers, it's okay. Yeah. Let's go to the stirrups. Stirrups, I want to have diameter 10 millimeter, number of legs, yeah, should be like that. Anchorage type can be like that. And I want to define this stirrup spacing 50, 300 millimeter and 50 millimeter. This means that every 50 millimeter can be a stirrup according to the required design. So I can also modify it if I want only here this one, then every 100 millimeter would one stirrup appear, and here every 50 millimeter. Okay, yeah, the next thing is the reinforcement layout. Here I leave the concrete cover as here, and I don't want to distribute the reinforcements along this slab over the complete slab, and also deactivate the distribute torsional reinforcement. And then we will calculate it. Yeah, the other things we don't need. Yeah, you will find more there in the online manual. Let's calculate it. Now, here in basic overview. Here in basic overview about the required reinforcement. Here and here, also some messages or notes. I click on OK. And now we take a closer look to the results. Members, and there I can see, first of all, deactivate it maybe. So first of all, the required one for the top. I think this is pretty clear because here we have some support moments, and then also for the bottom, here we have some field moments, and also for torsion. So this is, and now we set up the provided reinforcement here and here. Pretty nice. And we can also show us the rendering. It looks like that. Yeah, not bad. And yeah, this was so much about the design of this T-beam. And the next one is the column. Maybe I can show you something in addition. Because RF concrete members creates a reinforcement proposal, which is based on the required reinforcement and the reinforcement parameters. So when I go here to the provided reinforcement, you can see it here, and you can also print it to your printout report. This is maybe also interesting to know. And you have also the possibility to edit the reinforcement for sure. Yeah, you can set up the coordinates, locations, and so on. This may be interesting to know. What else? Yeah, of course, this 3D rendering is also possible. By clicking here, then you will have it an extra window. Yeah. Okay, and now, last but not least, the columns. let's do the columns. Therefore, concrete members again. You can also design the columns in the RF concrete members. So the Eurocode 2 provides 3 methods for the design of columns. The simplified method based on the nominal curvature, then the general method based on a nonlinear analysis, including second order effects, and the method based on nominal stiffness. And for our example, we will use the method based on nominal stiffness. So we don't have to use RF concrete columns. We have also an add-on module, especially for the RF concrete columns. But in this case, we use here this RF concrete members. So new type, columns. Columns, members, no problem. I can select them very easily, just here by view. And activate here all columns by filtering them. I click on OK. So columns. Now I did a short mistake. No, sorry, I'm really sorry. I have to do it again, sorry, because now I assigned the members to the wrong reinforcement template. So downstand beam. So now I create a new one. Here, this one, yes. Oh, I will copy it, doesn't matter. I choose all members, I click OK. Now columns, sorry for the confusing. And now I do here, exactly the same things like before. So I activate here 20 and 25 as diameters. Stirrups can be the same. Reinforcement layout. Here it's important to have this one. In corners, yeah. And also here you can set up the concrete cover and so on and other things. And the min reinforcement should be here. So when I want to add some secondary reinforcement, the maximum bar spacing should be 150. And the identical diameter as a longitudinal reinforcement should be here 12. Okay, then we can calculate it again. By far faster. And now we can see here also the required reinforcement again. And also here, because we are we have a big, very low normal forces in comparison to quite big cross section. Then we get also the message that here in this case, the minimum reinforcement for compression members was selected for this one. So take a look to the long reinforcement. Looks like that. Yeah. And when I take a closer look to the columns, I can see it here. So required reinforcement, provided reinforcement, I think this is clear now. Okay. This was our last chapter. Yannick, are there any questions maybe to discuss? Otherwise, I would show you our website.
I think the rest of the questions that came in were pretty specific, and I already answered them, so I think we can carry on with the website. Nothing
Okay.
we really need to discuss here, I think.
Okay, perfect. Okay, good. Then our website, first of all, here our homepage. Here you can find the most important news, trainings, also events, and so on. I would recommend you, because you are students, also here to take a look to our knowledge base. There we provide and publish every day new technical articles about useful functions in RFEM. Also, we give you an insight into the standards and so on. Also, a lot of things about FE mesh sizes or how to avoid singularities, something like that. This is everything there. We have at the moment almost 1,000 technical articles. So reading all these articles will take a lot of time, but then you are a really professional engineer. Okay, good. Yeah, what else? I can also recommend you, when you are interested in webinars and online trainings, take a look to the webinars. Here we provide once a month different webinars. The last one was about glass design and also blast time history, also interesting timber structures, and also free online trainings for students. Yeah, for students, and also paid online trainings for professional engineers. And the other one I can really recommend you is visiting, especially when you are using our software as beginner, our structure analysis models to download, and also our education platform where we have a big e-learning and infotainment. So structure analysis models to download, you can download more than 1,000 structural analysis models for free, really for free. And you can see how other engineers or other users have modeled them and applied the loads, did the design, and so on. Yeah, just click on one of this example. For example, give me one nice. Yeah, this wooden packaging here. This looks pretty cool. I click here and just click here on download, and then you can use it. And then you can take a look to RFEM. And also when you stay here a little bit longer, you can move it a little bit. This thing here looks also pretty interesting. Yeah. Okay. E-learning, of course, I can really recommend you visiting these videos, watching these videos. There will you learn a lot of things. And also, if you are interested in that topic, which are the most important formulas of a civil engineer, just click the video. I post the link in the chat, and then you can take a look to the video and comment it if you are some formulas are missing and so on. Good. Then we are coming to the end. It was very nice doing this training with you. I hope you enjoyed this training, you learned something, and I am really looking forward when we see us or hear us in the next training. Yannick, anything from your side?
Yeah, I had a lot of fun. Thank you for the questions, and I hope to see you soon or hear you soon again in one of our next seminars, webinars, whatever. So yeah.
Okay, so stay healthy and bye-bye.